In this unit, we are going to see what operations we can do with matrices. So we are going to see the addition of matrices, the multiplication of matrices by a scalar, by a number, and the multiplication between matrices. For this, we have to remember what a matrix is and know the operations between real numbers. So we will start by remembering that a matrix of order m times n is a set of m times n numbers that are arranged in m rows and n columns of this form. This form that we see here as a box of numbers. We will denote it as a capital A or a sub ij to simplify the notation in the calculation and in the operations. So for example, a matrix 3 times 4, 3 rows, 4 columns, a matrix 3 times 3, etc. Once we have remembered what a matrix is, we are going to see what operations we can do with them. The first thing we can do, and the easiest thing, is what we call the addition of matrices. Two matrices can be added if they are of the same order, and then they are added term by term. That is, I could do a sub ij plus b sub ij, always when a sub ij and b sub ij have exactly the same number of rows as columns. And so I add the elements one by one. For example, if I have this matrix 2 times 3, I will always be able to add any matrix of size 2 times 3, so that I will do 2 plus 7, element 1 by 1, minus 4 plus 1, element of row 1, column 2, minus 4 plus 1, minus 3, 5 minus 2, 3, element of row 1, column 3. As you can see, they add term by term, and this is the way to add. The operation of sum of matrices then, it fulfills that it is commutative. That is, the order of numbers doesn't affect the result. It is associative, that if I have to add 3 matrices, then I will add 2, and then the third, and it is independent of the order in which they do it, that the matrix 0 fulfills that I add the matrix 0 to a matrix, and it is exactly the same matrix, both in one way or the other, since it is commutative, the operation of addition, and that the opposite matrix makes that when a matrix is added opposite to it, it gives me exactly the matrix 0. These are the properties that the operation of sum of matrices, the typical properties of the sum in real numbers, and as you can see, also in matrices. The next operation is the product of a matrix by a number. How will we do it? Well, if I have a matrix, a sub ij, to which I am multiplying by a scalar alpha, any real number, then what we do is multiply each one of the elements of the matrix by that number. That is 6 times 2 minus 4, 5, 3, 0. 1 is the same as 6 times 2 equals 12, 6 times 4 equals 24, with the minus sign, 6 times 5 equals 30, 6 times 3 equals 18, 6 times 0 equals 0, and 6 times 1 equals 6. That is, all the elements of the matrix are multiplied by that number. Well, this is the other of the operations. The properties that satisfies are typical properties of the product of a number by a matrix or by numbers in general. That is, it is distributive with respect to the sum of matrices. That is, a number times a plus b gives me the same as the first to make the sum, and then multiply by alpha, which is first to multiply by alpha each one of them, and then add. The typical elimination of parentheses. Also the distributive with respect to the sum of numbers. That is, alpha plus beta times a is the same as alpha times a plus beta times a, the same elimination of parentheses. It's the same if I add the numbers first and then multiply by the matrix, or if I multiply first each one of the numbers by the matrix and then add them. The pseudo-associative, that is alpha times beta times a, is the same as alpha times beta times a. The order of the product will not change the result, and that by multiplying by the number 1, the matrix, it remains invariant. Of course, if I multiply by 1 each one of the elements, it remains exactly the same matrix. As you can see, they are quite common properties in the product of numbers. And the next operation is the most complicated, which is the matrix product, since in the matrix product, when I obtain a matrix A of size m times n and a matrix B of size n times p, the result will be a matrix also, as it happened before, but of size m times p, and whose elements are obtained in this way. Each element C, sub ij of the matrix C, is the product of the elements of the row I of the matrix A times the elements of the column J of the matrix B. A scalar product in which I multiply first element by first element, plus second element by second element, plus third element by third element, plus so on until the last element by the last element. That is the way the element Th sub ij, and thus for each one of the Th sub ij that makes up the Th matrix. As you can see, it is a little more complicated. Let's look at it with an example so that you can see that in reality it is not so much. If I want to multiply this matrix, which is of size 2 times 3, for this matrix, which is of size 3 times 2, the result will be a matrix 2 times 2, where the first element will be to multiply the first row by the first column. 1 times 3 plus 3 times 4 plus 4 times minus 1, as we have set up here. And that will give me the first element of the new matrix of the product matrix. The second element, as you can see, if I do all those operations, that is 11, a number. The second element is the first row multiplied the second column, that is the element of row 1 multiplied by 2, 1 times 1, 3 times 2, 4 times 3. I do all those operations and I get 19. The element of the row 2 column 1, well, row 2 multiplied by column 1, minus 5 times 3, 2 times 4, and 6 times minus 1, and I sum it up, and it gives me minus 13. And the element of the row 2 column 2, well, it gives me row 2 multiplied by column 2, minus 5 times 1, plus 2 times 2, plus 6 times 3, and that gives me 17. As you can see, a matrix times another matrix gives me a new matrix. C sub ij obtained in this way. Well, that is the way to make the product of matrices. As you can see, I have multiplied a matrix 2 times 3, a matrix 3 times 2, and the result has been a matrix 2 times 2. Well, this, what do you see here in red? This 3 coincides with this 3 is essential. To multiply two matrices, it is essential that the number of columns of the first matrix coincides with the number of rows of the second matrix, so that I can make the first row for the first column, for example, or row by column, without remaining elements. Then it is essential that these two numbers coincide, and the result is always I eliminate those two numbers, and I have the 2 and the 2. This 2 and this 2 can be the same or not, m and p. But always the n must be the same. The numbers that are multiplying the number of columns of the first must coincide with the number of rows of the second to be able to make the product. Otherwise, the product of matrices cannot be made. Well, what properties does the product of matrices meet? Well, it meets the associative. That is, the order that multiplies first A, B times C, and then multiplies times A, the same as that multiplies first A times B and then C. I cannot interchange A, C, B. That does not mean that the multiplication is not commutative. A times B and B times A can be different matrices, and even some of these two products cannot be made. It depends on the size of the matrices A and B. Then it is very important to remember that the multiplication is not commutative. If it meets the associative property, as we have said, it also meets the unit matrix. By multiplying it by a matrix A, both on the right and on the left, it gives me the matrix A, of course, on the right. And on the left, it will give me the correct matrix identity so that the product of matrices can be made. And it also meets the distributive with respect to the addition of matrices. That is, the elimination of parentheses. A times B plus C is the same as A times B plus C. These properties do meet them, but they do not meet the commutativity. And that is very important, because they cannot interchange the order in the product. Well, we have seen this. We have seen the three operations that we know for matrices: the addition of matrices, the multiplication of matrices by a number given to anyone, and the multiplication between matrices.